Hi everyone, my name is Jeroen Tyrion and I am the founder of TiNC Works. This video is the first in a series of walkthroughs and deep dives to get you more productive with the system. Today I'd like to show you how the results of a recurring measurement test are plotted and how you can manipulate this plot to get further insights. I've selected a few tests that we ran between Ireland and Belgium. A TiNC field unit was running as a virtual server in one of our servers on the Amazon EC2 cloud in Ireland, and the target was one of the Google web servers, located in the Google data center in Saint-Ghislain in Belgium. Both of these systems and their immediate network vicinity are very stable, so we expect to see very flat lines. Let's switch to the portal and look for the test results. The list of results of recurring measurements can be found in the menu under Measurements. Here you will see a list of all the tests that are performed by your equipment. The tests can be sorted in any way. For this video I created a bunch of tests which all run from the same unit towards the same target, and they all use the same instrument, namely the ping instrument. Some of these tests have been running for a very short time and others have been running much longer, or maybe with a reduced interval so that they've collected much more data. Let's start off with the test number 611. As you can see, the source is a unit in Ireland, the target is the Google server. We're using the ping instrument. It has been running for a day and a half at intervals of 300 seconds. And this is how the data can be presented. We're using the Plotly library, which has a whole bunch of very interesting features. When we're using the ping instrument, this instrument will generate 5 data series as it fires off 5 consecutive ping echo requests in a burst. The data series are available are the minimum time it took for the target to respond with an echo reply, the maximum time one of these requests took, the mean or average time of the 5 requests in the bursts, and the standard deviation over this collection of 5 requests. And lastly, the percentage of requests which went unanswered, called packet loss. As a recurring measurement is running, the results of each burst are collated in the field unit and stored on the TiNC Works service in the cloud. All tests are presented on the portal for inspection and analysis. Let's take a closer look at our first test, number 611, which ran for 32 hours late July. Clicking on a test in the list retrieves the dataset from central storage. This may take several seconds if the dataset is large, but the data is then cached locally. We're using the Plotly library to graphically display the test results. Most series are plotted in the regular way with the measured latency on the primary y-axis on the left. Data points from the packet loss data series are plotted on a secondary y-axis on the right edge of the plot. Data points with a packet loss of 0 are not displayed at all. From the initial presentation, it's clear that the path between the field unit and the target server is very clean, it's very stable. The traces for minimum, average and maximum overlap, and the trace for standard deviation does not show significant spikes at all. We can clean up the presentation even further by clicking on the legend to turn traces off and on. Like this, I will remove the average and max and the standard deviation. For now, let's look at the trace with the minimum detected latency. This trace is indeed very flat, generally meandering between 11 and 11.5 milliseconds, which is very good. By the way, the great circle distance between Dublin and Saint-Ghislain is less than 800 kilometers as the crow flies, so the absolute minimum time it could take for a signal to get from the field unit to the server and back is just over 5 milliseconds. The 6 milliseconds of extra time is due to the signal traveling through a fiber optic, which slows down the signal, the optic not being laid out very straight, and of course all the routers and switches in between. And by the way, without serious investments, a latency for this path of 11 milliseconds is as good as we might expect for a public internet connection. Anything faster than that is very expensive. The trace for the maximum latency is also very interesting. Let's blend that one back in. This shows that there are multiple tests which have resulted in significantly higher latency, in this case up to 19 milliseconds, as I can show by hovering the mouse over the trace. Plotly allows us to show all data points for a given sample or just the one nearest to the mouse pointer. That is here. Show closest data on hover, and we only get to see the one value. And there is our 90 milliseconds maximum latency. Or I switch to compare data on hover, and we get two values. And with more traces turned on, we get to see more values, and it starts to clutter up a bit. So let's take these out again and focus on the real message. Another interesting aspect of this measurement is that there were no ping replies lost during the test. A very clear indication that this path was indeed clean. If I turn off all the other traces, there is no packet loss. Let's move on to another recurring measurement test, running from the same virtual unit to the same Google server, but for longer. Test number 613. It's immediately apparent that there has been a significant event in the early hours of July 31st, perhaps even a service disruption. All traces show unusually high and varying values. We can use the Plotly facilities to zoom in on the plot. Shortly after 4:30 in the morning, all traces went erratic. I will hide some of them to get a clearer picture. The minimum latency begins to fluctuate, with spikes up to 41 milliseconds. What's more, one of the pings at 4:40 was lost altogether, showing up as a purple dot. Then at 6:50, everything stabilizes again. But at a much higher level than before, more than 24 milliseconds, more than double the normal value. This continues until 920, and then the regular level is recovered, 11.5 minimum and 12 milliseconds maximum. This whole event took 5 hours, and I'm sure that if there were users involved in traffic on this path in this time frame, they would clearly have noticed this. This concludes today's walkthrough of chart features as part of the TiNC Works system to monitor the health of your network. My name is Jeroen Thirion. Thank you for watching. Please contact us at www.tinc.works. TiNC Works. How healthy is your network?